It keeps running on my desk.
I need it back.
I know how to.
Okay, let's start out talking about the calculator. Now, we are eventually going to learn how to get the calculator to do a whole bunch of work for us, but for this class, it should only be in checking your work, not actually doing the work. But one thing that you want to do every day when you get your calculator, because you don't know what Algebra 2 did to them, that's Algebra 2's first period, and you don't know what they did to it, and you may be doing everything exactly right in the calculator, but it just won't work for you, because it's something they changed during Algebra 2. So every day when you get your calculator, you want to push the second button, the 7, second, the plus button, number 7, and then go over to all, we'll wait for you, Jason. We'll wait for you.
Watch out.
I need you to follow along.
Hey, you keep popping up on my hand to get it to.
So you do the second and then
Okay.
the plus one.
The second button, the plus sign, 7, go over to all, push enter, and then the number 2.
It came up something said, I know. I turned mine off so it would go away. And then I turned it back on, and now it says press alpha F1 to F4 to locate shortcut now. And do not show.
When it pops that weird thing up, you put the button and it goes away. Okay, so
Basically, what you do with it is that
Yeah. Alright, so you want to do that every day when you come in. You want to reset your calculator. This is the fastest way to do it. And if any changes were made first period or any time during the day before, then this will reset everything. It'll clear the memory, reset all the defaults to what they're supposed to be, so it will work nice and neat for us. Alright. 1 through 8. It was just simply determine whether each relation is a function. That means a yes or no answer on each of these. And the explained part was either going to be The x's don't repeat. The x's do repeat. Or passed the vertical line test, failed the vertical line test. Now this may seem real simple to you, and if it does, great, because there will be at least 2 questions on the STAR test involving this right here. For example, you might turn the page and there'll be a problem that has 4 of these mappings on it, and they're going to ask you which one is not a function. Or you may turn the page and there will be 4 graphs on it, and it might say which one of these is a function. Or they might give you 4 sets of points and ask you which one is not a function. I mean, out of 54 questions, you have to get 30 correct. And 2 of them could be just as simple as remembering what's right here. So number 1, is this a function or not a function? How do you know? The x's do not repeat. There's only one arrow coming from each number in the domain. The x's do not repeat. Do any of the y's repeat? Yes. -1 and 4. Does that make a difference? No. The y's can all be the same number. It doesn't matter. What matters is the x's. So on number 1, you should have yes, comma, the x's don't repeat. How about number 2? Not a function? Okay, so no, comma. Why is it not a function? The x's repeat right here. This is like your pay right here. If you work 6 hours, what is your pay supposed to be? Is it supposed to be 9 or is it supposed to be 10? There should be no guess. Number 3. No? How come? This 2 right here is the same as that 2 right there. Number 4. Yes, it is a function. Okay, I'm going to show you some examples out of the Algebra 2 book. It does a little bit better job of explaining what to look for. Why do you don't want to use special functions here? In Algebra 1, we typically do 2 types of equations. Linear equations, which make a line, and nonlinear equations. For us, that's going to mean parabolas, U-shapes. In a linear equation, everything is to the first power. There are no exponents written in any of these equations right here. That means that every term is to the first power. In nonlinear equations, here's a y that's raised to the second power. That means it's no longer a line. In the second one, the x is square rooted. That means it does not have a power of 1. And here we have multiple terms with x's in it. That means the x is going to end up on the bottom of a fraction in the denominator. And in this one, clearly, the x is in the denominator. Here are the types of equations that we want to see to be able to say, yes, it is a function, and then later on, yes, it is linear. This looks like the one that you just did, very much like it. It is a function. So yes. How about number 5?
No.
I heard yes. Okay, so explain. What kind of answer will you give if it's a graph? Has to pass or fail the vertical line test. So does this pass the vertical line test?
No.
It does here. It does here. Oops, it doesn't here. So the answer to number 5 is no. It's not a function. And we didn't stop and talk about it, but number 5 is an example of where you have what's called discrete points. Discrete. Anybody give me just a general idea of what the word discrete means? Say that again. I heard somebody over here say something. Not descriptive. Really? Anybody else? What were you saying, Ethan? The word discrete actually means kind of secret. If you're somebody's friend, they might tell you something and ask you to be discreet about it. That means you're not going to go tell everybody else. You're going to keep it in. Discreet. If you get in trouble somehow, the person that you're answering to may say, don't worry, we're going to be discreet about this, which means they're not going to let everybody else know. Discreet. Kept in. Kind of secret. In this graph, none of these points are connected to other points. They're all by themselves. A discrete place would be where you could go to be by yourself. Discrete. Individual points not connected together. Discrete. The other 3 graphs here are what are called continuous graphs. Continuous means that you can draw the graph without lifting your pencil off the paper. You could start right here, go this way, pivot right there, and continue down this way without ever picking your pencil off the paper. Right, Riley? You can't do that when you're plotting single points. You have to put your pencil down, make a dot, lift it up. Put your pencil down, make a dot, lift it up. Discrete, continuous. What would this one be? Number 7. Continuous. Number 8. Continuous. There are 3 continuous graphs here, 1 discrete. Here's the difference. When you're talking about information that can't be cut up, Now this is going to sound a little bit morbid, but it perfectly explains the difference between discrete and continuous. If you were going to talk about the number of babies born in Ector, Texas last year, there can't be a half a baby born. There can't be a quarter of a baby born. There can't be 3.5 babies born. That would be an example of discrete. It's either going to be no babies born, 0, or it will be 1 baby born, or 2 babies born, and it can't include anything in between. Not 3.5, not 6 and an 8, right? Right, Ethan? However, if you're talking about the number of cookies that Alexis ate, right? Now Alexis could eat no cookies, or she's definitely going to eat 1 cookie. She could even eat 1.5 cookies. Is that possible? Yes. She could eat 2.25 cookies. It is possible to cut that cookie up into sections. That's basically the difference between discrete, where you can't split it up, you can't section it, and continuous, something that you can talk about in pieces for cookie. Alright, number 6. It's a continuous graph, but is it a function? Number 6. Okay, yes. How do you know? Passes the vertical line test. No matter where you draw a vertical line, it's going to touch only 1 time for each vertical line. Now, would it still be a function if there were a dot here instead of an arrow? What if I drew my vertical line right here? Yeah, it could touch 0 places. It can touch once for each vertical line. But it can't touch more than once. So yes, passes a vertical line test. What about number 7? Yes. How come? That's not the test that we use on the corner. Passes the vertical line test. What about number 8? No? How come? It fails the vertical line test. Right, so I could draw a vertical line right here. It does not touch my graph at all. That's okay. That's not more than once. I could draw a vertical line right here on the y-axis, and it touches my graph 1 time. Okay, that's all right. That doesn't disqualify it. But as soon as I get to the right of 0, now it's impossible for me to draw any vertical line that doesn't touch this graph more than once. Fails the vertical line test. Woo! These are the kind that we have to get right when we go take that STAR test. We'll be doing some practice later on in the year. Come February, I'm going to whoop some of these out on you, and you're going to go, what? I ain't never seen that before. It can be just that easy. I'm going to give you some exercises to do here in a minute. We're going to talk about how to do them. Number 9, let's talk about it for a moment. The table shows the total enrollment in Texas public schools. The school year is on the top. The enrollment in thousands is on the bottom. That means you multiply this number by 1,000 and that's what the number actually is. How many zeros does 1,000 have? 3. So this number would actually be 4750, 000. What would it make that number? 4,750,000. Part A, it says write a set of ordered pairs representing the data in the table if X is the number of school years since 2008-9. These get a little bit confusing, but they generally follow the same pattern. X is going to be our input. It's going to go on top. Y is going to be our output. It goes on the bottom. X, Y. If it's the number of years since 2008-9, then in this very first column, how many years has it been since 2008-9? All right, today is September the 14th. Now, if I ask you, how many days has it been since September 14th? How many days has it been since today? 0. So the first input is 0. The output is exactly the way that they have it here. Okay, now it's 2009, 2010. So how many years has it been since this year? 1. 2010-11. It's been 2 years since the start. And then 3. So really, this is the way our table should have looked. Now, they didn't tell us to make a table, but I drew it out so that you would understand what we're going to do next. And I labeled it X and Y. So part A says, write a set of ordered pairs. Okay? Now we have the data that we actually need for our ordered pairs. It's a set, so we start with the set bracket. And the first point will be 0, 4,050. X is 0, Y is 4,750. Mm-hmm. 1, 48, 48. 2, 49, 34. 3, 49, 99. Close the set. So if I gave you exercise number 9 to do, this is what part A would look like right here. Now we did that so that we could do part B, draw a graph showing the relationship between the year and enrollment. Is a year something that you could cut up into sections? Yeah, you can cut a year up into sections, half a year, quarter of a year. So this is going to be a continuous graph. We can plot all the points and we can draw a line or a curve connecting all of them. Alright, so here we go. I'll get my paper up here where you can see it. Why do you think I drew it like that? Yeah, there's no negatives when you're talking about a date. Well, some of you, when you date, it's going to be negative, but with this, not so much. Ha, 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 ha. Anyhow. Alright, my years are 0, 1, 2, 3. So I can spread them way out here. That's my x's. 0, 1, 2, 3. Maybe I'll put a 4 down here just for good measure. Now my y values go from 4,750 all the way to 4,999. Here's some symbolism that you're going to see maybe on the star test. We're going to draw this little curly thing right here. CJ, how does it look? And here's what this means. This means we're going to leave off all of this that comes between these two numbers because it's just not important. I know, it seems crazy, but that's what they do. That's all that little symbol right there means. We're going to leave off all of this part of the y-axis because it's not important. 5,000. So 48, 49. There we go. Now we're ready to graph this. 0, 4750. So over 0 up to 4750. There's the first value. 1, 48, 48. Right there. 2, 49, 34. 49, 34. That's not going to be halfway. It'll be less than that. So maybe right around there. And then 3, 49, 99. It's going to be right under the 5,000. Continuous graph. It's not linear, it makes a curve. That's just beautiful. Let's sign that. Look, this could be on eBay tonight. By tomorrow morning, this live will be in the thousands. The original work of art. It's incredible. What does continuous mean? You can draw the graph without picking your pencil up off the paper. Continuous also means that it is something that you can cut into pieces. Money, time, days, weight, age, all of those things we can cut into pieces. Until you get to be 20-something, you're always going to say, I'm 15 and a half. I'm 17 and a half. And then you get to 20, and you're like, I'm not so excited anymore about being another year older. Right, Connor? Yeah. Alright, where we want to concentrate for the rest of the period, which we're not going to get to do, Good discussion today. Calista, tomorrow don't talk so much so we can get something done, okay? Alright, thank you. Please sanitize the calculator. Is that continuous or discrete?
It's on.
Purple.
I don't know. You probably can actually draw without picking up the pencil.